In this video, I'll show you how to create ripples like those seen in this pond, made entirely with grease pencil and Python. Along the way, we'll also learn a few algorithms that come in handy when creating geometry with code. I use this video by Ravindra Godbole as reference, which gives us a clear sense of the structure of the ripples and how they move. I'll include a link below in case you want to see the full video. After analyzing the footage, I came up with a list of things to replicate. We'll want 3 to 10 rings per ripple. The rings seem to stack up or compress more on the leading edges. The inner and outer edges of the ripples seem to fade off slightly. And after a while, the ripple gets less intense and slowly fades out. With this list in hand, the first thing we need to do is build the rings of our ripple. In this case, the code we use for generating circles will be a nice jumping off point. I'll include a link for it in the description. We'll start in 2D animation mode in Blender, split the view, and create a new text file. Then we'll paste the circle code into it. We'll start by getting rid of the extra call to the ellipse function, since we'll only need one ring for now. Then we'll run it to make sure it's still working. Remember, with this code you should have a grease pencil stroke already in your scene and have it selected for this code to work. Before we get started, there's a couple of housekeeping things we need to add here. First, because we're going to be using a vertex color to shade our strokes and not materials, we need to remove all the materials from our grease pencil strokes. We'll do this by calling the clear function on the data material slot. Next, we'll want to make sure that we have explicit control over the grease pencil's line thickness. For this tutorial, we want the lines to be drawn in world space. To do this with code, we'll add a line after our G-pencil definition, and we'll set the stroke thickness space attribute to world space, all caps, no spaces. Now if we run it out, the circle turns gray because we've cleared the materials, and if we zoom in or out, it scales appropriately. Now we're ready to start building the rings of our ripple. To begin with, we'll create variables to hold the number of primary, leading, and trailing rings. We'll also add a couple of variables to hold our ring size and spacing. These default values should be good for now. Create a function called buildRings. We'll pass it our grease pencil frame as the first argument, followed by the center point position and the size we want it to be. After that, we pass values for the number of main, leading, and trailing rings, and the ring spacing, which will tell it how far apart we want the rings to be from each other. The first thing we need to know is exactly how many rings we're going to build, so we'll simply add the number of main, leading, and trailing rings that have been passed in. Then we'll add a loop for every ring R in the total number of rings. Since our rings will potentially start quite small at the beginning of our ripple animations, that is where the drop hits the water, we want to make sure that we handle the situation where the size could be less than 0. We'll add an if statement so that if the size is less than or equal to 0, we'll pop out of the current loop. If the size is greater than 0, we'll create our ellipse with a call to the ellipse function. After that, we'll add a line which iterates the size of the rings by subtracting the ring spacing value from its current size. In this case, we're using the minus equals so that each ring gets smaller as we go until we get to 0, at which point our if statement stops it from building any more rings. And lastly, we add the call to our shiny new buildRings function. Now we can run our function and should have 7 rings. Of course, it helps if the default value of the ring spacing variable is a more reasonable 0.05 units. Now that we have the rings working, let's turn our attention toward the wave compression. Currently, our size change from ring to ring is linear. That is, if we plot out each ring's size, it will produce a line. But in this case, we want our values to be non-linear. We want the ring spacing to start off fairly small and then ramp up quickly to a larger spacing. Luckily for you, I've got just the ticket. I've created a Python script which can be used to test various methods of iteration on a simple line. I'll include a link to this so you have it for reference. To run it, we'll create a second text file and paste the script in there. Since we don't want to ruin our current ripple grease pencil, we'll switch to object mode and create a new grease pencil object and make sure it's selected. Then we'll hide our original ripple to get it out of the way. Now if we run this code on the new grease pencil, we get a line that moves upward. I'll leave you to peruse this reference script on your own, but in brief it contains codes to generate a grease pencil line as well as 3 helper functions, norm, lerp, and remap. And then further down in the code we call the line function, and below that, where there are a lot of commented lines, are the various formulas that we can experiment with to generate each point's vertical position. By default, the point's z position equals its x position. This is a linear function. Since our x values are normalized to be between 0 and 1, the z value simply increases in value between 0 and 1, producing a line that slopes upward to the right. But something interesting happens if we comment out that line and uncomment out the next line. In this new line, we take the x value and we raise it to the power of 2. If we run this, the line is no longer straight, but it slopes up gradually. This is an exponential curve. Increasing the power to higher values causes the rise to become more sharply accentuated. The other expressions in this section use various algebraic formulas to generate different types of slope that move in different directions. The one that seems the most useful to us here is the fractional exponent. Back in our Ripple code, we'll start by adding a variable to hold our wave compression values. In this case, it'll be our fractional exponent. Next, we need to normalize the r iterator to be a value between 0 and 1, so we'll borrow the function from our line reference script and use it here. Down in our build rings function, we'll normalize the value for r based on the total number of rings we're building. This way, no matter how many rings we want to build, the value here will always be between 0 and 1. We then just need to adjust our size as we iterate through the loop. In this case, we'll still subtract the ring spacing from our size, but first we'll multiply it by the wave compression value we get from our calculation, which is exponential. In order for this to work fully though, we need to adjust our loop so that we're counting from 1 to the number of rings plus 1. Because 0 raised by any exponent equals 0, this would result in the first two rings being stacked on top of each other. So by starting our counting 1 later, we'll avoid this. My original plan to generate the smooth peaks and troughs of each wave was to use a combination of line thickness and hardness settings on each ring, but this didn't work out well. The result looked decent enough when facing the camera, but looked horrible in a perspective view due to the line thickness. Instead, the approach I decided to go with was to create multiple rings for each wave, peak, and trough, each set to the appropriate intensity to create a smooth sine wave effect. This means we'll need to add more rings to our ripple in between the current rings so that we have some resolution to play with. To implement this in our code, the first thing we'll need to do is to import a new variable from the math library called tau. Tau just means 2 pi. This isn't absolutely necessary, but it does clean up our code a bit. Next, we'll add some variables so that we can calculate how many total rings we'll need. The steps per ring variable will hold the number of rings we want between each peak. This will act as the resolution of each wave. And add a numPeaks variable to make clear the distinction between the number of peaks in our ripple, previously the number of rings, and the total number of rings, which is now the sum of our peaks times the steps per ring. We'll need to take into account the extra rings used for resolution. We'll do this by dividing the old ring spacing code by our new steps per ring variable before subtracting it from the size in each loop. If we run it now, we should get a lot more rings. But before we do that, we need to comment out our total ring calculation inside the build rings function first. Currently it looks like just a solid blob, but each ring is there. We just need to make some adjustments to the line thickness, which we'll do shortly. Now that we have the extra lines to play with, we can start trying to build the wave effect to our strokes. To do this, we'll use a sine function to drive each ring's strength attribute as we build it. To start with, we'll add some variables to control our strength ramp. We'll start by adding vars to indicate the min and max values we can have. Next, we'll add an angle variable to drive our sine function. If you need a refresher on using sine functions, check out my video on making circles where I explain this in detail. Typically, we would give this a default value of 0, but because of the way we're going to build our wave function, we want it to start at the lowest point of the sine function output, which would be pi plus half pi. The angle step will be used to indicate how many times we want to cycle through the sine function. So in this case, that would be the number of peaks in our ripple. We multiply it times tau, which gives us the angle of each peak in radians, and then we divide that by the steps per ring to get the angle for the final resolution. And lastly, we add a variable to allow for explicit color control of the ripple's peaks. We'll just use white for now with a full-on alpha. In our old approach, we simply built a single ring for each peak, but in our new approach, we'll make a series of rings that gradually fade away in the troughs and fade up at the peaks. We'll do this by setting the strength attribute of each ring's stroke as we create it, based on the sine function. Before we get into calculating our values, I made a helper function that takes care of applying the color and strength of our rings. This function is pretty simple. It takes stroke, color, and strength as an argument, and applies those values to each point in the stroke. This makes it relatively easy to control the stroke's appearance without the use of materials. To implement this for each ring, we'll start by passing in our starting angle to the build rings function. We'll be feeding the sine function our current angle. As the angle increases, the sine function returns a value between -1 and 1 for every 2 pi, or tau radians, we feed it. This continues to oscillate between those values as the angle increases. The grease pencil stroke, on the other hand, requires a value of between 0 and 1, so at the very least we'd want to squish our values into that range. This is a perfect case for using the remap function in my reference script. We'll pass the remap function the sine of our angle. We know that the output of the sine function will give us a range from -1 to +1, so those will be our first range arguments. For the range we want it to remap to, we want that to be the limits of the strength attribute on the stroke, which are 0 and 1. Once we have the value, we can add a call to our setRingColor function and pass in the computed values. We'll also want to add a line that iterates our angle by the angle step, so that as each ring is built, we continue moving to the next step with the sine function. Now we can try it and see what we get. At first glance, it looks like something is misfired, but if we switch to edit mode, we can see that the rings are actually there. This makes sense though. Our rings are white and our background is white, so we can't see them. To help with this, let's add a second grease pencil object so that we have something in the background. Go to Add, Grease Pencil, Blank, and then switch to Draw mode and use the Rectangle tool to draw a rectangle a bit bigger than our frame. Go to the Material tab and turn on Fill Color and make sure the alpha is set to 1. Since black is a bit harsh, let's soften that up to a gentler blue. Now we can discern the rings, but they're still pretty much a blob of white. This is because our line thickness is set to a constant value of 20, so they're all stacked up on top of each other. Ideally, we want the line thickness to be driven by the distance from one ring to the next, so let's add some code for that. Just before the call to the create circle, let's make a variable for line thickness. Because we want the size of our lines to be driven by the size of the ring, we can borrow the snippet of formula we used for calculating the size earlier. 1 unit of line appears to equal 0.001 meters, or 1 millimeter. Knowing that, we can go back to our formula and multiply the size of our ring calculation by 1,000, the number of millimeters in a meter. There's one minor issue here though, which is that the results of the formula are quite likely to produce a float value, but the stroke's line width attribute is expecting an integer. We could simply cast the results as an integer, but by doing so, Python's default behavior is to throw away the fractional part and thereby round down. To avoid having any unwanted gaps in our rings, it would be preferable to round up when we cast it as an integer. Thankfully, there's a command called ceil, short for ceiling, in the math library. This casts the number as an integer, but it rounds up the value. Once we've imported it, we can wrap our function in a call to the ceiling function. After that, we can add an argument and parameter for line thickness to our circle function. The last thing we want to do before we run the code is just a bit of housekeeping. In build rings, in its current configuration, we're defining the R norm and WC variables near the end of our loop. But our line thickness formula uses those values further up in the code, so we need to move those up front so that Python won't complain. Now we can run our code and see what we get. It looks better, but the rings are getting clipped by the background plane we've created. So we'll switch over to object mode and adjust the background grease pencil's Y translation to push it well behind our ripples. This is now functional, but to make it more flexible, rather than to remap the strength values to the default 0 to 1 range of the stroke's strength attribute, we could instead pass in our strength min and strength max variables here. The nice thing with this setup is that we can control the minimum and maximum opacity values of the rings just by changing the strength min and strength max variables. Now we have some pretty nice looking ripples that also look good at an angle. The next thing we can try and do is to tackle the fading off of the ripple's opacity at the leading and trailing edges. We'll start by adding a variable that we can use to control the strength as it fades out. Then down in the build rings function, right after our current strength calculation, we'll add an if statement that kicks in if the rings we are building are less than the number of rings in the leading edge. Remember, we're building 10 circles per ring, so we need to multiply it by the steps per ring to start fading at the right place. Inside the if statement, we'll multiply our current strength by an additional formula to make it fade on. We'll take the R norm value, remember this is a value between 0 and 1, and we'll raise it to the power of the taper strength. The trailing edge is a little more complicated. Since our R-norm values are near the top of our range, we want them to taper down exponentially. Looking at our reference line script, the formula that would work best for this appears to be the 1 minus x to the power of 2, which would taper down from 1 to 0 smoothly. The only trouble here is that that formula requires a whole number exponent, while we're currently using a fractional exponent for the leading edge. To make it so that we don't have to create a separate variable for the leading and trailing edges, we can convert the fractional exponent to a whole number by dividing 1 by it. Now we have a nice fall off for the leading and trailing edges. Before we go further, it's worth doing a bit of optimization here. We're generating quite a few strokes for each ripple, which isn't too bad when doing a single frame or single set of ripples. But ultimately, if we want multiple ripples with animation, it could start to get quite heavy. One simple way to do this is to avoid building any rings who end up with a strength of 0. After all, if the strength is set to 0, they won't be visible anyway. We'll add a variable which you can use to control the threshold strength at which rings are no longer being created. In the main loop, we'll move the call to the ellipse function just before the set ring color call. That puts us in a better position to evaluate the computed strength before we decide to create the circle or not. Then we'll add a switch that only builds the ring and sets its color if the strength is greater than 0. To verify that our script is working properly, we'll also add a ring counter to tally up the number of rings we're building and print them to the shell. We'll remove this print statement later since print statements can dramatically slow down your code. The rings are looking pretty good, but it would be nice to be able to control the ring sharpness as well. We'll add a variable to control our sharpness and give it a starting float value of 1.0. Then down in the build rings function, after our initial strength calculation, we'll adjust the strength by raising it to the power of our sharpness variable. If we try and raise our strength to a value of 0, it'll produce strange results. So we'll make sure to skip this calculation if the sharpness is set to 0. If we run the code now, nothing happens, because raising a value by 1 gives you that same value. But if we drop the value slightly, it starts to change the trough to peak ratios. Likewise, we can increase the number beyond 1 to get a different result. We can even get into negative numbers if we wanted to, but the best results for sharpening seem to come between a value of 1 and 10. Now that the ripple has the look we want, it's time to put it in motion. There are two things we need to do. First, we need to scale up the rings over time, and then at some later point begin to fade off in opacity. We'll add variables to specify the starting frame of the animation, how long we want it to stay at full strength, and how long it takes to fade off. Next, we'll add some variables to control the speed. In the video I was referencing, Mr. Godbole measures the speed of the ripples and comes up with a value of 14 millimeters per second, so we'll use that as our value. In order to calculate the scale rate, we need to specify how many frames per second we'll be using in Blender, and then to calculate the rate we simply divide the speed by the frame rate. For the opacity fade-off, we'll add two variables. One is the default starting opacity, and the second we'll use for our iteration function. In my previous tutorial on animating grease pencil objects with Python, we developed a handy function that checks for the presence of an existing frame. We'll borrow that function and add it to our script to save time. Lower down in the main body of our code, we'll need to adjust how we handle the frame in order to animate it. Up until now, we've hard-coded our frame to 0. We also were clearing the layer before we generated new strokes. We'll remove both of these lines. We'll now build more than one frame by stepping through the range that begins on the start frame and ends on the frame, which is the sum of the start frame, duration, and fade duration. Inside this loop, we'll use a setup we've used before, where we use our getFrame function to test for the existence of the current frame. If it doesn't exist, we'll create one. If it does exist, we'll just clear it. Up until now, we've been building our ripples at a scale of 1, but ripples will always start at a single point where the drop hits the water, so we'll change our ring size variable to have a starting value of 0. Once we reach the end of our ripple's duration, we need to start fading it off, so we'll add a switch that kicks in after the start frame plus duration. A linear fall off here felt a little bit weird, so I opted to use an exponential curve for this. We start by normalizing our current frame number to a value between 0 and 1, and then we adjust the opacity exponentially. In this case, I'm using the formula 1 minus the frame to the power of 2. In order for our new opacity calculations to have an effect, we need to add the opacity parameter to the build rings function. In build rings, right before the optimization part of our code, we'll multiply the strength times our opacity value, and now our rings can fade out over time. Because our rings will be fading to 0 over some duration set by the user, a good optimization would be not to bother to build rings if the opacity reaches 0. To do this, we need to have the build rings function report how many rings it builds. We can replace our print statement that tells us how many rings we're building and just have it return that value instead. In the frames loop, we'll add a switch which only works if the number of rings built is greater than 0. This means that once the rings fade off completely, the code will stop building frames. Another potential issue is that during the first few frames, our rings might be so small that a new switch would stop the ripple from being made before it even got started. So we'll add a check here that states that if the current frame is less than 5 and the ring equals 0, we'll just let it build one ring during that time. The last thing we need to do is add an iterating variable for our ring size so that it increases each time by adding the current ring size to the rate. Now if we run it, our ripples are animating outwards. From here, it's just a matter of tweaking our variables to dial in something that looks good. Now that we've successfully built one ring, we'll reorganize our code so that it can create multiple rings. We'll start by creating a makeRipples function. For this function, we'll only pass in the variables we want to control externally, such as the number of rings or the start frame. There are a few variables that will not change per ripple, such as the ring size and opacity, so we'll move those variables into our new function. In the end, I decided to place each ripple on its own layer so that its timing could be adjusted independently from the other ripples. Since we'll be adding code later to manage things at the layer level, we'll just add a bit of code here to clear out any existing frames on the layers Python object. We can also remove the code for testing the presence of a frame and just create one based on the current loop. The last thing to do is add a line to the main body of the code that calls our function. And after fixing a few typos, we can check out that the code still works. It should behave exactly as before. In order to generate a bunch of ripples like a rainstorm, we'll need to rely on some random generation like we've seen in previous tutorials. We'll start by importing the random library. Since we'll be putting each ripple on its own layer, we want to make sure to clear the existing layers so that we don't end up with bogus data from previous runs. We'll also add a variable for how many rings we want to create. To make things more reproducible, we'll also set the random seed with a value. The number you use here isn't terribly important, but it allows the same randomness to be generated each time. That way, if you get a result you like, you can repeat it if needed. We use random functions to generate float values for each ripple's x and z position, start frame, duration, and fade duration. Remember, we use random.uniform when we want a float value, and randrange for integers. Next, we'll make a new layer per ring so we can separate them out, and the user can adjust the timing on each ripple individually. So we'll make a name for each layer to be the word ripple, plus the number of the current loop, and then we'll call the new function on the layer's Python object and pass it the name. We'll also pass in the setActive=true flag so that the layer becomes active after being created. If we run it now, we can see that multiple ripples are being created just on top of each other. That's because we forgot to pass in our new random x and z positions to make the ripples function. Now we have ripples. From here, it's a matter of finding the settings you like. Oh, and we'll probably need more optimization. Clearly our runtimes are increasing dramatically now because we've got a lot more ripples, so there's a few things we can do to improve that. To count the time, we'll import the time module and then use its perf counter function to record the time the script was run. And then down at the bottom of our code, we'll query the time again, but subtract it from the original time and print that out as the total runtime of our script. To count the number of rings, we'll create a numRings variable at the beginning of the main body of code, and then at the very end, we'll cycle through all the layers and all the frames so that we can print out how many rings we've made. If we toggle our shell output, we can now see that with 100 ripples, we're generating about 57,000 individual strokes, which takes my computer about 10 seconds. As a first pass, I went back and reduced the number of rings and the steps per ring, and this helped a lot, bringing my total strokes in time down by almost half. Another area that could use some optimization is the duration of each ripple. Currently, the script creates the stroke and the frames that lie beyond our scene's time range, which is pretty wasteful. So in our makeRipples function, we'll add a line which only builds the frame's ripple if the current frame is less than the last frame in our scene by referencing the frame end attribute on the scene's context. And with that, our tool is now ready to use. Creating the pond scene is pretty straightforward. I created an image of the pond to use as a background and imported it as an image into Blender. By default, the ripple plane is in the vertical orientation. Switching to object mode and rotating it by 90 degrees lays it on the ground. One nice thing is that our code is generating the strokes in the grease pencil object's local space. So even if the plane's orientation is changed, the strokes will regenerate in the right orientation if we run the script again. We can reposition our grease pencil object to get the ripples where we want them, and if we don't like the randomness, we can change the seed and try it again. We also can eliminate specific ripples by deleting their layers, or we can slip their times if we want. And that's about it. Overall, I'm pretty happy with these results, but I suspect there are a lot of other ways of doing this. Let me know in the comments if you think of any. Thanks for watching.